Okay, so let's get started. So today we'll finish Chapter 3, the virtual work in D'Alembert's principle. There's only one section left on that I want to cover. And then we'll do some examples, and I think Michelle, the TA, was going to join and walk you through a couple of examples, and then we'll also answer questions on the assignments. So the first part will be a short lecture, and then we'll do some problems, and then we'll answer questions on the assignment. So let's start with a summary. Oh, it's possible I have to leave for 2 minutes in the middle of the lecture, but it's unlikely. But I'll just give you a heads up that might happen, and it'll be brief. Okay, so we've looked at the principle of virtual work. And this was a method of handling statics. And so the principle of virtual work says that for static equilibrium, the total virtual work on a system is 0. So the sum of all the virtual works done on the system equals 0, where a delta work, a virtual work, I, is the virtual work done by some force with some arbitrary virtual displacement. And the reason this is nice is that we only need to consider forces that can do virtual work. And so what that means in general is that we can typically ignore internal forces. So that's in contrast to, the vectorial approach, where you would have to have, in order to have static equilibrium, you have to consider all of the forces and all of the torques. And the sum of all the forces and the sum of all the torques are 0, and you have to include all the tension and normal forces and reaction forces, etc., to solve the problem. So this is actually a much more simple way to solve it once you've gotten used to the strategy of setting up generalized coordinates and generalized virtual displacements. Okay. After that, we introduced D'Alembert's principle, which was the subject of the last lecture. And what D'Alembert's principle basically says is that if one considers, I'm going to say in quotation marks, the force of inertia, then any system can be treated as if it were at rest. So you take Newton's second law, you define this force of inertia so that the sum of the forces now, F plus I, is equal to 0. And so then, because now this is like a statics problem, you can apply the principle of virtual work. And so what we did is, we did the virtual work, which was the virtual work of F plus the virtual work of I. And then we did quite a bit of mathematical manipulations to arrive at the result that d by dt of di t by di qj dot minus di t by di qj equals capital Qj, where this is true for all j. So there's one equation like this for each degree of freedom Qj. T is the total kinetic energy of the system. Capital Qj is the generalized force in the j direction. And then Qj is lowercase qj, a generalized coordinate. Oops. And so these are all scalar quantities, right? Qj ultimately becomes a scalar. Kinetic energy is easy to calculate. And so that's the D'Alembert's principle. Any questions about that? Oops. Okay, so one issue is that in D'Alembert's equation we have this T, the capital T for the kinetic energy, and we're taking derivatives of capital T with respect to Qj dot and Qj. So that means we want to be able to make sure that the kinetic energy T is indeed expressed in the coordinates Qj so that we can take the derivatives. So, oops. Want to make sure that T is expressed in terms of the generalized coordinates which is the set of the QJs. So for example, maybe the QJs are spherical coordinates, because we found that the system is much easier to describe in spherical coordinates than it is in Cartesian coordinates. So if we want the kinetic energy in terms of r, theta, and phi, that means we have to convert a half m times x dot squared plus y dot squared plus z dot squared. That needs to be written in terms of some kinetic energy that depends on r, theta, phi, and presumably r dot, theta dot, and phi dot. Right. So if I can always write easily the kinetic energy for a particle in Cartesian coordinates, because it's x dot squared plus y dot squared plus z dot squared. But when I go to take the partial derivatives in D'Alembert's equation, I need to be able to say what is di t by di theta dot, for example. So it means I need to be able to express the kinetic energy in terms of whatever my generalized coordinates are. Okay. So this, I'll show you the general strategy, and I may or may not assign it on the next week's assignment to work it through. So let's look at the general form. So T, the kinetic energy, is the sum over all particles of a half mi ri dot squared. So that's the same as the sum from 1 to n of a half mi, and then I'm going to write the ri dot as dri by dt. That's just saying that what the definition is of ri dot. Now I am going to expand this in terms of our generalized coordinates. So let me write the first dri by dt. So that's the sum from j equals 1 to n. So it's the sum now. I'm breaking this out in terms of the generalized coordinates. So I have di ri by di qj, qj dot, and then in principle, ri could also depend explicitly on t. Then there's a term di ri by di t. And then I rewrite the second term, so that was the first dri by dt. And then the second dri by dt looks exactly the same, but of course it needs to be a sum over a different index. So let's sum from k equals 1 to lowercase n, and then it's the same formula, di ri by di qk now, qk dot plus di ri by di t. So now I have the sum plus a term times the sum plus a term. And so that's the messy part. But hopefully it's not too difficult to convince you that once you carry out this whole sum, you're going to end up with 3 types of terms. So the first type of term you're going to end up with is something with the sum from j equals 1 to n times the sum from k equals 1 to n of some factor, which I'll label ajk, times qj dot qk dot. That is going to be the result of multiplying a half mi, the first sum term, and the second sum term. Is going to give something that's going to have a qj dot and a qk dot in it. And it's going to have, you know, some complicated thing out front, which I'll just call ajk. Then there'll be a second term that'll be first order in the qk dots. So that'll be a sum k equals 1 to n of bk qk dot. And then there'll be a constant term. Or it's not necessarily a constant term, but a term that doesn't depend on the q dots. So for example, so this gives us, so let me just say, write the last line here. This gives us what we wanted, right? This is now t as a function of q1 to qn, q1 dot, qn dot, and in principle t as well. So for example, in Cartesian coordinates, because that's easy, so in Cartesian coordinates, q1, q2, and q3 would be x, y, and z. And so I can just pick out the formula for the kinetic energy that we have here with the ajk's, the bk's, and the c, and compare it to the kinetic energy I have up top here for Cartesian. And so then what we find is that ajk is equal to a half mi, and then I'm going to introduce what we call the Kronecker delta. So delta jk is what we call the Kronecker delta. And the Kronecker delta is equal to 1 if j equals k, and it's equal to 0 if j is not equal to k. So what this is saying is that ajk is equal to a half mi if j is equal to k, and it's equal to 0 otherwise. So it means a11 is equal to half mi, a22 and a33 are equal to half mi, and then all the other combinations, a12, a23, are all equal to 0. Does that make sense, everyone? This is the first time you see the Kronecker delta? Or? So for Cartesian coordinates, then we have a11 equals a22 equals a33, and then all other ajk equals 0. And then similarly, there's no term in the Cartesian version of the kinetic energy that has a single q dot in it. They're all q dot squareds. So bk and then there's no constant term, and c are both 0. So note, oops, if di Ri vector by di t equals 0, then T, kinetic energy, only has the first term in it. And we say that, so that means that Vk equals C equals 0. And we say that T is quadratic in the velocity. So let me do another simple example of this. In polar coordinates, the kinetic energy is a half mi times r dot squared plus r squared theta dot squared, or phi dot squared in this thing, plus z dot squared. So in polar coordinates, where we have Q1 equals R, Q2 equals phi, and Q3 equals Z, then we have, again, first of all, only AJK terms in here. Right? We don't have BK or C terms in there. They're all quadratic in the velocities. And so then we have A00, that's equal to a half mi. Oops, 0, 0 should be 1, 1. Right, that's the term that's in front of r dot squared. Then, again, we only have terms where j equals k. Right, there's no r dot, phi dot. So A22 is a half mi r squared, and A33 is a half mi. So this is quadratic in the velocity. Okay, so any questions about that? Alright, so I'm going to leave the example to be done later. And I want to look at conservation of energy. So let me rewrite D'Alembert's principle. We have d by dt of di capital T by di qj dot minus di capital T by di qj equals capital Qj, where capital Qj equals the generalized force in direction J. So let's consider a specific case now for these forces. Let's consider the case where the applied forces Fi are given by the gradient of some potential function. So that means that forces can be obtained from the gradient of a potential. Okay, so if I write this as a vector that in Cartesian coordinates, then I have minus, and then the gradient, remember, is the gradient of a scalar function gives a vector, right? So that'll be di by vi by di x hat plus dvi or di vi by di y hat plus di vi by di z hat. Right, just like gravity. Gravity is potential, and you can take the gradient and you get the force of gravity. So let's calculate now the virtual work done by such a force. So delta W will be the sum from y equals 1 to n of our Fi's dotted with delta Ri's. So that'll be equal to minus the sum from I equals 1 to capital N. So the Fi I can write as a gradient. So that's grad Vi dotted with delta Ri. And if I plug in what we had, that's the sum from I equals 1 to N of, there's a minus at the front, sorry. So we have di Vi by di x hat plus di Vi by di y hat plus di Vi by di z hat, and that's dotted with delta of, if I write my Ri vector in terms of Cartesian coordinates, then it's just x hat plus y hat plus z hat. So that's minus the sum from I equals 1 to n of di vi by di x delta x plus di vi by di y delta y plus di vi by di z delta z. And now that's just delta v expanded. So that's the same as saying minus I equals 1 to n of delta v. Right. If delta v is a function of x, y, and z, then di vi by di x times delta x plus di vi by di y delta y plus di vi by di z delta z is just the variation of vi. So, in other words, the virtual work is the negative of the virtual potential. So if you go back to your vectorial mechanics, that's like saying the work is the change in potential energy. It's really just the same equation with deltas with lowercase deltas instead of capital case deltas. So this is it's like the work done is the change in potential energy. So for that specific case, right, for the case where the applied forces are given by the gradient of some potential, negative of it, then we can rewrite D'Alembert's principle to say, instead of the sum from I equals 1 to n of the applied forces dot delta Ri minus the sum of forces I equals 1 to n of mi Ri double dot dotted with delta Ri. Right, this term is the inertial force term. So that's D'Alembert's principle. That's what we started with at the last lecture. I can just replace the first term with delta v, and since it's a negative delta v, that'll kill off the minus sign that I have between the two terms. And so I can rewrite this as the sum from I equals 1 to n of the virtual changes in potential energy plus the sum from I equals 1 to n of our mi Ri double dot dotted with delta Ri. Okay, so we're going to reuse that form of D'Alembert's equation in a second. So furthermore, we're going to consider an even more specific case. We consider the case where delta R is equal to dr. So we choose a virtual displacement the direction of the true displacement. So we can do that, right? The virtual displacement has to be in harmony with the constraints. We're allowed to choose any virtual displacement that we want, and so we can obviously choose the one that is also the displacement that the system will take. Okay. So, more specifically, we choose the case when delta Q equals dQ. So we choose that the virtual displacement of the generalized coordinates is the true displacement of the generalized coordinates. So this does not necessarily imply that delta R equals dr. Maybe I'll just remove the first sentence because that's just going to be confusing if I read it like that. So we consider the virtual displacement to be in the direction of the true displacement, and we choose that in the generalized coordinates. All right. So now, in general, Ri is a function of Q1 to Qn and T. Right. So only if di Ri by di T equals 0, so only if R doesn't depend on T when it's expressed in the generalized coordinate, then delta Q equals dQ implies that delta R equals dr. So delta R equals dr only if di Ri by di T equals 0. So we're choosing only the specific case where the position vectors of the particles and the locations where the forces are applied don't depend on time when you express them in terms of generalized coordinates. And so the same thing can be said of V. So we have delta V equals dV when delta Q equals dQ only if di V by di T equals 0. So, in summary, we consider the case where the forces are given by a potential. We choose the case where the delta Q are equal to the dQ. We choose the case where di Ri by di T is equal to di Vi by di T equals to 0. So that means, this last point means that delta R is equal to dr and delta V is equal to dV. So let's apply this now to Dalember's principle. D'Alembert's principle tells us that the way we just wrote it, the sum from I equals 1 to n of the delta V plus the sum from I equals 1 to n of the mi ri double dot dotted with delta ri, that's got to equal to 0. Right? So that's equal to. So now we choose delta r equals dr, right? So the first sum is going to be the sum from I equals 1 to n of the dv's plus the sum from I equals 1 to n of mi ri vector double dot dotted with dri vector. Now this last term I'm going to multiply by 1. And I'm going to write the 1 as dt divided by dt. Okay. So that gives me the sum from I equals 1 to n of dv plus the sum from I equals 1 to n of mi ri double dot vector dotted with, I'm going to take the dt that's in the denominator, so I have a dri by dt, which I'm going to call ri dot, and then I'm still left with the dt from the numerator. So that's equal to the sum from I equals 1 to capital N of dv plus the sum from I equals 1 to capital N of, so here I have r double dot dotted with ri dot. So you agree that that's the same as a half m d by dt of ri dot squared dt. Alright, if I do the chain rule to ri dot times ri dot, I'm going to have a term that's ri double dot times ri dot plus ri dot times ri double dot. I'm going to have two terms that are the same, and they're both ri double dot times ri dot. Okay. So that's the sum from I equals 1 to n of dv plus the sum from I equals 1 to capital N of a half m. And now I'm just going to cancel the dt's again. I'm going to say that's dri dot squared. So that's the sum from I equals 1 to n of dv plus the sum from I equals 1 to n. So I can bring the half m into the d, because the half m is a constant. So it's d of a half m ri dot squared. And that's the same as dt. I guess I forgot to say the i's everywhere on the v as well. So there's one potential force V on each particle. So now this is going to be, let me just put it as the sum over one thing. So it's the sum of I equals 1 to n of d of vi plus ti. And I can move the d outside of the sum, so it's d of I equals 1 to n of vi plus ti, and that's the derivative, the differential of v plus t. Well, v plus t is the total energy, all right, because that's potential energy and t is kinetic energy. So what this tells us is that v of v plus t is equal to, if we go back to the top, this whole thing is equal to 0. So that means that the integral of v plus t, which is equal to v plus t, obviously, is equal to a constant, and let's call it E. So I've just argued that T plus V is the total energy of the system, right? T is found by taking the sum of the half MIRI dot squares. And if you sum all of the kinetic energy of the particles, you get this total T curve. And V is the same. V is the potential energy of particle I. And it's the force Fi, which is the net force on particle I, written as the potential. And so we know that that's potential energy. So the sum of the potential energies of all the particles is the total potential energy of the system. So V of the total energy of the system is 0. And that means the total energy of the system, once you integrate that, is a constant. And so what we've shown is we've shown conservation of energy. And we'll show conservation of energy many more times. And so energy is conserved, but of course we have to remember our conditions here, right? The net force on each particle must be able to be written in terms of the gradient of the potential. And then the other important thing is that the potential doesn't depend on time. So think about it. If the potential energy changes with time, so if gravity is stronger in the morning than it is in the evening, then energy is not conserved, right? If you have a simple machine that's based on a perpetual motion machine where there's no losses, and it's just a ball rolling up and down a slope, if gravity changes with time, then the energy is not going to be conserved. All right, so any questions about that? So we wanted to do some examples from the notes, but then I think there's also some questions on the assignment.
Yeah,
so I guess I'll leave it up to Michelle to take over now.
Not sure how to connect the OneNote. It's
so
kind
Michelle,
of awkward,
connected?
but actually, what questions do you guys have from the homework?
I've allowed you to.
Oh.
So let's see if you can screen share first. So somehow I have to stop screen sharing myself on it first. So Michelle, now you should have a link at the top left of the gray screen that says Start Sharing.
Okay, it says application has stopped.
And then it should open up a window where you
sharing.
can choose which window you would like to share.
And that's what's happening. I clicked sharing, but it says the application has stopped.
I think I've off. Nothing's happening?
Yeah. Well, here, request elevated privileges. Maybe that's what I need to do.
Application sharing has stopped, right? Let me try on a different
Yeah, you did.
computer here. Yeah, I thought I gave them to you, though. Okay, so I think you have to click on the gray panel, the second button, the one that has two windows on it.
Okay,
and
I
just
never
below
get
that,
the
it says Start Sharing, and if you
second
click
window.
that, it should open the second window, and then you can choose what you want to share.
I'm clicking on the double window, and it says Application Sharing, and then I never get a drop down or anything.
Yeah, then.
No.
But just below that, doesn't it say Start Sharing?
Okay. All right.
But it works for R2, which is me on a different computer, logged in as a student.
It says waiting for applications sharing to start.
And we give you the privilege.
So maybe it's just a really slow connection.
So if you click the
waiting for application sharing to start.
That's pretty snappy on the other computer, though.
Well, I have a page from the Blackboard.
Oh, what happened?
No, I don't.
Yeah, but now if you click the middle thing, and you click Start, you don't have a Start Sharing at the top left of the gray area. You're on a Windows computer.
Well, there's the regular page.
Let me turn it on.
Yeah, I can. I practiced it yesterday. Yeah.
Yeah, I don't know if you can write very legibly on it, though.
Let's see here.
Oh, yeah?
You guys can see that? Can everybody see? Okay. It's a little awkward, and I don't know how to make the screen go forward.
Yep.
You know, to the next page, but we can start. So now that we know that I can write, what are your questions? No, that's the weird part. That's what it said there should be. It just says public page.
There's a new page button at the top, isn't there?
Oh. Well, it went weird. Okay.
No, but I have a new page button.
I don't know.
Let me see what happens
when
I click it. We can't get back to the previous page now, can we?
Okay. Will you undo so that it's a nice curve instead of that?
I have a little scroller at the top where I can add more pages. So you just ask me when you want another page.
Oh, okay. Well, right
I don't know why it changed like that.
here.
All I did was go back
Well,
and forth.
then there
between
we're
the
back
two
to,
pages.
okay.
I don't know why it completely changed the location of them. It's weird that the screen sharing is not working though.
Okay. Why is it doing that? Oh, okay. And now it won't do a delete. Why won't it do delete?
Well, that's probably just me pressing buttons.
There. Okay. So would you guys pipe in and tell me what your questions are, and I'll see what I can do for talking about the problem. Questions on assignment 2? I have silence. So we'll talk about 3.5. Let's see here. On 3.5, I guess how I like to start everything when I'm working on a problem is I read, oh, I don't want that. I read the problem over, and then I draw a picture. And maybe other people can think about these things in their head, but I can't. And so I draw a nice picture. And here I have weight 1. And then I want to be higher. Weight 2. And what this does when I do this is it kind of allows me to think about the problem as I go along. And sometimes I really take my time so that I can thoroughly consider, oh wow, this is bad, but you guys kind of know what I'm doing here. What's going on? Sometimes just thinking about the problem is the best thing that you can do, because I'm going to try to do the center. Wow, that is bad, bad, bad. Okay. I will get better, I promise. There's B. So let's see here. So first off, I want to think about the constraints. And the most important thing to do when you're trying to learn physics or solve a problem is to have an effective algorithm. And Dr. Martins provided us with a really good algorithm. The only part that he missed is step 1, draw the question. Step 2, identify the unconstrained number of degrees of freedom. So we have 2 particles, we have 2 coordinates. How many degrees of freedom do we have? Yeah, 4, exactly. Thanks, Shane. So we have, let's see if I can do this again, degrees of freedom, 4. Well, that's awesome, but I have some relations here that I know I can apply. And the first relation that I can think of is the 2 different masses, mass 1 and mass 2, that normally I'd have to consider, I can describe with just mass 1. So I have at least 1 constraint, and then I look at the problem some more, and I say, well, the location of the 2 blocks is constrained by that string L. So somehow on that hemisphere, if I know the circumference of the hemisphere, and I do, I can describe it by the length of string. And then I say to myself, well, if I know that I'm on a hemisphere and I know the arc length, I can describe the position of both of these blocks through a single angle. So now I have 3 constraining equations and 4 total degrees of freedom. So when I add these up, I end up with 1 degree of freedom. Any questions? Okay, so then we go on to 2. And I say determine the number of holonomic constraints and write them out. Oh, I kind of already did that. The constraints are M1 is definitely going to be proportional to M2. Because we know M2 equals 2M1. So we can just talk about M. The location is related by L, and phi is related to theta. So I'm going to go to number 2 and relate phi and theta. I could go to a next page.
Okay, I can make a new page.
Or
new page.
I wonder, can I copy that picture, or did we lose the page? We didn't lose the page. You could go back.
It looked kind of ugly last time we went back. There it is.
Let's see if I can capture the picture.
So you don't have...
There's a reason you put the picture at the top of your, your homework or whatever. Let's see now. How do I copy? No, that wasn't copy.
Oh.
Maybe I can just drag it down.
I gave you moderator privileges.
Oh, hey, there we are. Hit page, delete page, view page, clear page. Awesome.
Well, now, see if the sharing works.
Yeah.
You have a start sharing button?
No.
What?
It's waiting for sharing application to start.
But you don't have in the top left a start sharing button. There's
No.
something weird with your version then, because it works for my other computer.
Follow me. Okay. This is a Toshiba. It's about 2 years old.
Yeah. But it must only be the Java. Well, we can try this offline. I guess we'll have to deal with the whiteboard for now.
Yeah. Okay.
You can control the pages.
Yeah. All right, new page. We'll try this. Control V. Okay, well, it didn't do it for me. So you guys kind of know. Oh, whoa, okay. You know what the picture looks like. You can look at your notes. I'm just going to kind of do what I need here when I need it. So we are relating phi to theta. And to do this, we need to know the arc length. Come on. All right. Okay, so S, which is typically the arc length, CR, and this is theta. That's C. And you know that there's a box here and a weight there, and they're connected. So arc length. Well, so for the first arc length of R1, we see that this is going to be R theta. And the second arc length is going to be R B. Okay, I have our, oh, okay. I saw all kinds of red and I wasn't sure what was going on. Just interrupt me. I mean, hit your talk button and talk, because that's probably the best way until I get used to this media. So I know that the length is equal to the arc length 1 plus arc length 2. So I say R theta plus R phi is equal to L. I pull out the R and I get theta plus C is equal to L. You see where I'm going with this? So now I know that my L over R is equal to, let's see here. Oops. Oh, I want to do that. I want to say that's minus theta is equal to C. So let's see, we go to a new page and a new idea, and my take home here is therefore, if I take d theta, it's going to be equal to or we can say that d theta is equal to d c. They're actually not related to what I just did, other than, yeah, they are. Sorry, I lied. Theta is equal to, come on, L over R minus theta. If I do the differential, I can see that d theta is equal to a negative, d phi is equal to a negative d theta, because this is a constant that we can find easily. All right, so number 3, we want to choose a general coordinate system. Let's clear that page. Okay, fine, then just give me a new page. Okay, so I have my picture. This is R1. Does everybody understand that I'm not talking about the radius, although it is kind of the radius? That I'm talking about the vector that relates them? I hope so, because you guys are silent like the grave. Okay. So I'm going to talk about R1. So we see that this line right here is R. And we can see that this is phi. So we kind of extend our line. We're going in the x direction up here, and we see that how we identify the x direction for R1, it's a sign because it's opposite. So I'm doing R times sine theta. Then I need to know what the y component is. Well, that's clearly a cosine because it's adjacent. So now I'm going to do a cosine. Then I do R2. Okay, so I've gotten a little bit lazy because this is really hard for me to write. There should be an x hat here, and there should be a y hat here, just so that we keep things straight. So now I have the R2, and I do the same thing. I extend it so I can see what's going on, and I say, well, again, I have a sign, except I am in the opposite. I'm in the negative direction of x. So now I'm going to say that this is R times a negative sign. And this time it's a phi and plus. Cosine is in, or rather, y is in the positive direction. It is an adjacent line, so it is cosine. V, and I'll do some of this just so that you understand. Laziness versus being thorough. Now when I take the derivative, I get a cos theta minus a sine theta. Don't forget the d theta. Now I'm taking the derivative of the negative sign, and that gives me a negative cos plus the derivative of a cos Now we remember that dc is equal to a negative d theta. Oh, man. Okay. So now I'm going to say that this is equal to, and I'm going to get rid of some negative signs because I can. And this changes to a theta. All right, so now we have done step 3. We've described our coordinate system, and we've written our transformation equations. That's what these guys are called. Now, we need to identify the forces that perform virtual work. And the deal about virtual work is, generally speaking, things that are horizontal don't do any work, and things that vertical, at least in our system, do work. So we're only going to consider the y component. I wonder if that'll help. Yeah, I think it will. Okay. So we're going to rewrite the virtual work equation just so that everybody remembers what this is comprised of. And that's a dot, sorry. So I have equals a minus mg r sine. And remember, I'm picking out only the y components from our transition equations. So I'm going to set this equal to 0. That's an equal sign, not. And I'm going to pull what I would consider a little shenanigan on you. I'm going to get rid of everything that's not in the parentheses by dividing it to the other side. And, of course, that 0 divided by all those constants. Oh, that's wrong. Sorry. Sleeping at the switch. and the R needs to go out here. So let me just rewrite. Don't write what I just did. Write this. Get the R out there. I'd encourage you guys to try this on a tablet. I mean, holy crap, this is kind of hard. Plus sine phi. And then we have this little d theta out there. And I'm going to commit my dirty trick like I promised. And I'm going to get this sine theta, come on, plus sine phi. And now we're going to recall what phi is. Because we've identified phi earlier. We know that phi is equal to L over R minus theta. So, okay, new page. Come on. So now we have 0, that's a 0, equals sine theta plus sine L over R minus theta. On your favorites page in your computers, put trig identity and choose your favorite site, because you use trig identities every day and it makes the math simpler. And you should be, I mean, I don't expect anybody to memorize it, because who would? The computer you look up. But definitely have it on your favorites page so that you can look it up easily and get your homework done in a timely manner. And I'm just relating this trig identity for you so that you know what I'm doing. Oh, come on. My hand is all locked up and numb, and it's because I'm nervous, so I hope you guys are enjoying this. Let's see here. Now we want to divide by cosine, so I'm gonna relate this for you. You know that sine theta stays the same, and then of course now we're going to put in our identity. And bless your hearts for staying. You guys are just delightful, although you're very silent, and that scares me a little bit. Let's see here. Now we're going to do this over R, and then sine theta. So now basically we're going to divide everybody by a cosine theta. You know, and I honestly thought about this, you know, what would motivate you to do this? And the only thing that I could think of really that would motivate you to do this is you need to somehow come up with a solution for theta. And in this particular configuration, there's no solution that's easily acquired. And so you're forced to think about, well, maybe if I have a tangent, I could do like maybe an arctangent at the end. And that might work out for me. So it's kind of before you know how the solution ends, that's a thought, you know, just kind of thinking about it. So of course, we have sine LR, and this goes to 1. And then we have a cosine LR, and this goes to tangent. So now I can pull a tangent out. That sounds kind of nice. Maybe. Something might work out here. Yet. And I get a 1. And let's see here. Minus cosine Oh, I did something wrong here. Oh, I know what I did. I'm sorry. Wait just a second here. I had a minus up there, way back at the beginning. Oh, you guys, I am so sorry. How do I go back? Okay, here I go back. Oh, no. There, okay. Let's see here. This is why you have notes to go off of. You can find your mistakes. Minus mg, so I'm taking my minus mg out of there. Well, where is it? I take my minus mg out of there, and oh, you guys, how did you let me get by with this? Up at the top, next page, back one. This is a negative. Here we go. This is a negative. You guys let me get by with it. Nasty. You guys need to catch my mistakes like that. This is a negative. Although it's a positive when I pull out that. Let's see here. I end up with, okay. Oh. No, that doesn't work. All right, I lost a negative sign up here. Sign. Sign. There is a 2. That's what I did. See this 2? I dropped it. I don't see how to erase. So I have a 2 there. That's a negative, all right. Got a little crazy with my cursor here. I just
It looks like Michelle dropped out, maybe? Let's give her a few seconds to reconnect. She might not have noticed just yet. In the meantime, if you guys have questions about specific questions about the assignment 2, which I thought there was in the discussion thread on the forum, maybe we'll wait till Michelle is done with the example, but you should ask those questions at the point of the tutorial. The midterm is on the Thursday, which is like the 26th of March, I think. It's wrong in the syllabus, but it's correct on the web page. Yeah, March 26th. Yeah, originally I had scheduled it during the spring break. Obviously I have to change that. For 2, hold on, I'm just looking up the question. What was exactly the question for 2-3? Yeah, so for problem 2-3, you can just follow the notes. The main difference is that when you're taking the delta W's, or the delta L, right, you're going to end up with a sum over I, because L depends not only, in the notes, we made L depend on only one function, Q, which we actually use Y. So there's only one Q dot, and the T. In the example, or in the problem in the assignment, L depends on Q1, Q2, all the way to Qn, as well as Q1 dot all the way to Qn dot nt. So when you do the variation of L, the delta L, you have to end up with, let me just screen share that until Michelle comes back, if she does. So for problem 2-3, we have L is a function of Q1, Qn, Q1 dot, Qn dot, and T. So when we do delta S, which is delta of the integral of L dt, you're going to need a delta L term. And so the delta L term is the sum of di L by di Qi delta Qi plus di L by di Qi dot delta Qi dot plus di L by di, no, there's no dt term. So essentially you're going to end up with the same math, but you're going to end up with like something with a sum, and then hopefully you'll have a Qi, so I guess you'll have the Qi inside of the sum. And so then you'll conclude that it must be true for all I. So you're going to have some term in here, let me call it squiggle. So then you'll have this sum of squiggle times that you can factor out of the delta Qi, and it must be true for all delta Qi, hence squiggle will be equal to 0. And here you'll have to integrate by parts. So it's basically just copying the derivation that's in the notes, except that you have to carry the sum through. Is that a high level enough explanation, or did you want more details? Do we have any other questions on the assignment? There's a couple questions on the first problem. All right, let's do 2-4 then. Quick start. Look up. So in 2-4, you need to find the stationary value when L depends on y prime, that we've done that before, but now it also depends on y double prime and x. So here it's going to be a similar strategy. I think Michelle is trying to finish marking assignment 1 this week. So here again, you're going to need delta L, and that's going to be equal to di L by di y delta y plus di L by di y prime delta y prime plus di L by di y double prime delta y double prime. So you're going to end up with this thing here in the integrand. So remember, delta y you can write as epsilon phi of x. Delta y prime, if you just take the derivative of that, that's epsilon, which is a constant, and then it's phi prime. And then delta y double prime is equal to epsilon phi double prime of x. So then you're going to have an integral. Oh, I guess the other point is, remember the integral is, it's a definite integral, right, with fixed endpoints. So we also have that phi at xa equals phi at xb. The variation is 0 at the endpoints. And similarly, the derivatives will be 0, and I give that. And then you're left with an integral over delta L, right? And delta L is that thing that we have up there. So we have di L by di y epsilon phi of x plus di L by di y primed phi primed of x. I'm going to just put the epsilon at the front here. Plus di L by di double primed phi double primed of x dx. And then you just kind of have to follow the strategy. So this will be delta I, the strategy that we used in the notes. So in the notes we had the same problem, but we only have 2 terms in parentheses, whereas here we have 3. So the first thing you have to do now is to get rid of this first term. Hi, Michelle. Sorry, I hijacked the session quickly to answer a question about the assignment. So let me just finish answering this question, and then I'll give it back to you. So what we did in the notes, right, we first got rid of the middle term by integrating it by parts. So here we have to first get rid of the last term by integrating it by parts. So the integral by parts, right, of u dv is uv minus v du. So the way we do this is we take the phi double prime to be the dv and this one to be the u. And so that means when you do the integral by parts of the last term in red, you're going to get a uv term, so that's a di L by di y double prime. And now the integral of phi double prime of x is phi prime of x. And then minus an integral of v, which is again phi prime of x. And then you're going to have a d by dx of di L by di y double prime, right? That's the du. So then you're going to take this thing here, and you're going to put it in here. but you're going to note ahead of time that this term here, I forgot to mention, this is from XA to XB, right? The constant term. But phi prime at XA equals phi prime at XB equals 0. So this term is actually going to be 0. So when you put the box thing back in here, you're going to end up with 2 terms times the phi prime, right? So you're going to have the first term, then you're going to have inside of the integral, right? You're going to have the di L by di y prime phi prime of x minus phi prime of x d by dx of di L by di y double prime. So you'll be able to factor out the phi prime of x here, and then you handle these 2 terms by parts, again, with dv equals phi prime of x. And you can sort of see by inspection that up here, right, you end up with a d by dx for the du term. So you're going to end up with a d by dx of di L by di y prime. You're going to end up with a d by dx of di L by di y double prime. So that's how you're going to get the d squared dx squared. Is that a good enough overview for problem 2.4? I don't want to give it away completely. I feel like I almost did. All right, back to Michelle. Are you able to? Oh, but I have to re-give you extra permissions.
All right. Let's see. While I had computer issues, oh, come on, where are the rest of us? I found my negative sign, so I need to go back up and fix a little something here. Some blank pages, because I'm just like that. I added these parentheses late, and the truth is when you pull out a negative sign and you have a positive term, you have to have a negative sign to go with it. Where am I? There we go. So once I pull the mg out, the negative mg, then this has to become a negative because you recall up at the top. Come on. Where are you? Oh, that's forward. Okay. We had it was plus. So, all right. So now that I found my pesky negative sign, let's see here. This becomes a negative sign. This is a negative sign. I have blank pages. I don't know why. I'm just, there we go. Negative. Now, this guy comes in here, and I have a 2. This is a negative sign. So I'm going to carry the 2 out throughout when I divide by cosine. So I have a negative sign here. I have a 2. This becomes a positive, and I have a 2. So now that we've made my corrections, we can proceed. I'm pulling tangent theta out. So this is a 1. Okay. This is a 1. Cosine 2 L over R minus 2 sine L over R. I'm going to take this to the other side. I have a tangent theta, and for time's sake, I'm going to go ahead and divide by this. And if anybody is lost by what I just did, please holler and I'll break it up. I know how hard it is to pay attention for this long, and it's easy to get a little bit confused. So now that I have this set up, I can take the arctan, and then of course I take the arctan over here. And that would absolutely give me theta, which is what the question asked for. So, new page. Now that we know what theta is and everything, we can dissect a little bit more from this problem. We can get the generalized force, and that's in the notes too. That's in our, let's see here. There we are. I just backed up a line before I did all my arctans and everything to describe the generalized force. Now, are there any questions? Because I had a lot of interruptions, and this is very new to me. Just giving you the general equation. Okay. We really don't have time. Oh, yeah, we do. I looked at the wrong clock. What time does the class end?
Well, it's supposed to end in 2 minutes.
Oh. I would give you an example of D'Albert's principle, but I can't do it in 2 minutes, especially with my writing. Do you guys have any questions?
Well, I can take up that example during the...
Well, I would be available Tuesday if you needed me.
It'll be okay.
Okay.
There's a question, is that Q phi on top?
Oh, yeah, that's Q theta. Oh, on top it is Q theta. Sorry. My phi's are cool little curly Q things that have a tail.
And there's only 1 degree of
My
freedom.
thetas are usually like that. I don't get sloppy like this because then they look too much like that.
Do you have, they're also asking when the assignment will be graded, assignment 1.
Oh yeah, I'm sorry. I'm hoping that I will have the assignment graded and back to you on Tuesday.